All right, let's do some more work with the information retrieval application. If you recall, originally we had a program called docterm.mumps. The code is in the video for this, and basically it read the collection, which consists of a title followed by an abstract. The abstract's about 20 lines long, and we create some global arrays. The first one is dict. It's a vector. Or dictionary is what it means. It's indexed by word. So what we get in dict is the total number, the value stored at dictionary or dict for a given word is the total number of times the word occurs in the collection. Total number of times the word occurs in the collection. That's important, because a different way of saying that we'll get to in a minute. Then we create the document term matrix, where the rows are the documents and the columns are words, and the values in the cells are the number of times the word occurs in the document. And finally, a vector called title, which is indexed by document number, and it's the title for document number X, whatever document number X is. We only did 2,000 documents, which is a small number. We want a larger number to really get good statistics, but for purposes of example, 2,000 is fine. By the way, I posted a link to my website where you can get the original collection. They're a collection of abstracts and titles from computer articles from the late 80s. Anyway, we process each document and title as it comes in. In the process of processing them, we remove punctuation. There's this translate down here, and we convert everything to lowercase. That's the processed document, and that process, those words after they've been processed, no punctuation, and everything in lowercase, those are the words that get stored. Now that creates things like if the original thing was 386-based, which was a common thing back then, 386 processors, the hyphen would be removed and you'll end up with 386-based as one word. That's fine, because when you retrieve and somebody types in 386-based, you'll do the same thing and you'll end up with one word with no hyphen. So the internals sometimes look weird, the words that we actually store, but that's okay, because we're going to do the same thing on the query side. So it all, comes out in the wash. I made a couple of changes here. There were minor errors. First of all, I put this if w equals empty, quit. That wasn't there. That resulted in a spurious extra word being printed out at the end, an empty word being printed out at the end of the display. It didn't affect the results, but it was just an empty word at the end. You needed the quit here. The other one is I think originally I didn't have a halt here. The halt is necessary, otherwise you go into the subroutine, but by this time line is empty, so it doesn't do anything anyway. And the quit at the end of the subroutine doesn't actually return because you didn't really invoke a subroutine. It's just open code. And in mumps, an internal subroutine is open code, and just regular code, unless you actually invoke it with a do. Since it's not being invoked as a do, you're just passing into it. The quit just becomes a quit for the program. The program terminates. All right, so that's docterm.matrix, .mumps, excuse me. The other one, well, the next one was, I've got them actually up here, dict.mumps. I'm hitting up arrow. In dict.mumps, we just printed out the dictionary. The dictionary is done at this point. We just print it out. And we print out the count first, followed by a blank, followed by the word. Okay, that's count, blank, word. We then sorted it. We sorted it, and with the output of that went into a file called, and here's the file here, word count. I sorted into word count in reverse order. So the most frequent came out at the top and the least frequent at the bottom. I don't have that original file right now, but the output of dict was run through sort, and the output of sort was then piped into or redirected into word count, which is what you're looking at. The most frequent word was that. Which should have been, I would have thought, but anyway, it's a small sample size, so we're not getting really good statistics. Anyway, in word count, we picked an arbitrary cutoff of about 400. Anything above 400 we left in the file. And then we moved down to the lower end. Anything with a count of 4 or less, we removed. Everything, we left. Anything with a count of 4 or less, we left in the file. Anything between 400 and 4 400 as the upper limit and the number 4 as the lower limit, we delete it. So what we've got is a file. It's actually a fairly long file. It's 12,293 lines long. That's how many words are in it. There's a lot of one-off words in here. This is our stop list. These are the words we're going to eliminate from the document term matrix. These are the words we don't want. They're very high frequency words and very low frequency words. Now we're working with a very small data set, so the statistics aren't good. Zenith and Zilog probably shouldn't be in here. I mean, I can delete them here. If I delete anything from here, it is not in the stop list, and the corresponding word will be in the final result. So there goes, and Zortek was something, Zilog, Zenith. So now they're in the final round. Xanadu, I don't know about Xanadu server. I see anything else down here? VT220, they were popular in their day, but you can go through here and manually do this. I'm not going to worry about it, but because we're just doing an example here. Or you can add words of your own. For example, I could add the word "the" in here. Just remember, if you do add a word, you'll have to put a number in front of it. It doesn't matter what the number is, because it's going to be ignored. But the format later on expects to see a number followed by a blank followed by a word. Okay, so I'll write that out and go back here. The next thing after that was word prune. Word prune.mumps. We zap out the vector, which will be our stop list. We open that previous file, and we start reading it. And what we do is we take each of the words, which are the second thing on the line, delimited by a blank, the second thing on the line, hence $piece, line, blank, comma, 2. That pulls off the second thing, which is the word, the first thing being the number. We put it into a vector called stop. So stop is indexed by a word. The value stored there is nothing. It's empty string. We don't care. All we need to know is W in the stop list. It's just a binary. Does it exist or does it not? So we build the stop list, close some stuff, just switch over, and then we went through for each document DN, for each word W in document DN. We extract out the word for in document DN. If the word is empty, we're done. That's we asked the question: does the word exist in the stop list, in the stop vector? So if W exists in the vector stop, the value of $data will be true. It'll be non-zero. It'll be true. In which case, we want to kill this instance from the document. So I am killing, if you remember over here, we kill that instance, that word in that document. And we also wrote it out to figure out, to let us know that we were killing stuff. Okay, that was word prune, and now we're ready to go on. And we're going to have to go through and make sure, a couple of things we need to do is, did any documents become empty? Is it possible that a document consisted only of words that were in the stop list, and therefore the document exists but the words are gone? We want to delete those documents. I don't know if there are any actually, but it could happen. The other thing is we want to calculate an importance. The simple fact that a word occurs, so many times in a given document doesn't necessarily tell me if it's an important word. Some words are very frequent. They occur in a lot of documents, and they're just barely indexing terms. Other words are quite unique, and their usage is going to be very clustered in a small number of documents. Even though their count is small, their importance is high. So do we have a way of ranking this? And there's a famous one called the inverse document frequency ratio. It's basically the log of n, where n is the total number of documents, divided by the number of documents in which an individual word occurs. So if some word W1 occurs 10 times in a collection of 1,000 documents, it's 1,000 divided by 10. You take the log of that. And you can take just about any log you want. And here I'm doing log 2, log base 2. You can do log base 10. Depends upon your counts. The logarithmic is a logarithm is essentially to smooth out the results so you can get wild swings in it. There are no specific units. It's entirely empirically derived. This technique works extremely well, surprisingly, and it's obviously very easy to calculate. But in order to do it, I've got to have a document count. for each word. How many documents does each word occur in? That's different than the number of times the word occurs in a collection. We want to know for each document how many documents it occurs in. Okay, and that would be a program I've written called dt.mps. I'll post it at the bottom of this video. First of all, we get rid of two previous vectors, dt and idf. idf is going to be the inverse document frequency weight for a word. It's the weight of the word in the collection. Okay, we set the document count to 2,000. That's where we were. And we start going in from 1 to 2,000. And we ask the question, $order up arrow doc, oops, I left out something there, up arrow doc, comma, all right, yes, that was omitted. So in other words, I'm asking what's the next word, the second column is the word, in document D. If the so-called next word, when you provide an empty string to order, that means it'll give you the first word. Okay, if there is no first word, if this vector is empty, if there are no words now left in this vector, you'll get back the empty string. So if the empty string comes back, it means that this document hasn't got any words anymore. Okay, so if I do the order and on document D and the empty string, and I get the empty string back, no words. So I want to kill the document. We don't need this document. Document, unfortunately, just consisted of words that were too high or too low frequency. You may want to print it out and look at it later, but anyway. So I kill the document D and I decrement the document count. There's fewer documents now. We need to know the total number of documents later. Otherwise, I start going through for each word in this document until I run out of words. And I ask, now I've got a word in a document. I ask if this word exists in the document count. This is the actual document count vector. If it exists in the document count vector, I increment it. If it doesn't, I establish this word in DT with the count of 1. So since a given word on this row only occurs once, if I find an instance of a word on a document row, that's an instance of a word occurring in a document. So I increment, or create it if it hasn't been seen yet. So when I'm finished here, DT, the values in DT for given words, will be the number of documents in which each word occurs. Excuse me. Right? So if it does exist, you increment it. If it doesn't exist, you establish it or create it with the value of 1. And when we're finished, DT for a given word will tell us how many documents the word occurred in. All right. Now we go through for each word. Now we don't care about the documents now. We're just talking about the words. For each word in DT, all right, until we run out of them, we want to set the IDF value for that word, the inverse document frequency weight for that word, equal to, I'll skip the justify. There's the document count, which may not be 2,000 anymore. It might be lower, divided by DT for that word. So say if some word occurs in 5 documents. Okay, so it's going to be DC divided by 5. Whatever the document count is up around 2,000 or less. And DT is some value which is obviously less than 2,000. I don't think there's any word that occurs in every document. But the words left over should be occurring in relatively few documents. That's why we got rid of the very high frequency ones. We also got rid of the very low frequency ones too, as you recall. Okay, so that value here, we then take the log base 2. Zig log 2 is my version of the base 2 logarithm. Okay, you get the base 2 logarithm. The problem is logarithm gives you a whole bunch of digits, most of which are meaningless. This is a very arbitrary calculation, so I decided only keep 2 decimal points. So we'll get a number and a decimal point and two digits to the right of the decimal point. The 1 here is the total field length. If you put 0 or 1 in here, it just means use what you need. It's not if I said 10 in here, it would have a field of width 10, and everything would be right justified in that field of width 10, and there would be leading blanks, which I don't want. So I just put a small number like 1. This here is important. The second one, that's the number of digits to the right of the decimal point to retain. And if you don't put that in, you'll get a lot of them. And this is not this is a good indicator, but 2 digits is all it really is good for. All right, then I write it out. I write out the IDF first, followed by a blank, followed by the value of the dictionary vector. That is the number of documents in which the word occurs. Number of documents in which the, back that up. That is the total number of times the word occurs in the collection. Dict is the total number of times the word occurs in the collection. dt is the number of documents the word occurs in. And finally, the word itself. Now, the IDF value we're calculating is the weight of the word in the collection as a whole. Doesn't tell us about the weight of the word in any given document. It tells us, relatively speaking, how important the word is in the collection as a whole. Okay, let's write this out and see if we can make it work. First of all, I'm going to remove key.dat and data.dat. So I start with a fresh database. Next, I'm going to do doc.term.mumps. And this will, I can call it, I'll send it the output to a file instead of flashing by on the screen. This takes a little longer because it's a longer process. Hopefully it's about done now. There it is. And if I look at docterm.text, well, VI, not VU. Actually, there was one once named VU. And that's what they look like. There's the title, and there's the words, and the numbers in parentheses are the number of times the word occurs in the abstract. You can say like apple. This is about apple, and it occurs 3 times. Apples occurs once. We gotta be nice to be able to have, find stems. So we have apples and apples, apple merged to one. Computer and computers and things like that, but that's another question, another problem. Somehow that got in here. I thought that was going to be removed, but anyway, we'll have to take a look at that. And anyway, that's what it looks like. Oh, it hasn't been removed yet. We have at this point in time, we've not done our stop list. Excuse me. That is the next step. I'm not going to do I can do the dictionary thing, but it'll overwrite the value in word count, though that file word count. Well, it wouldn't. It just write it out to the screen. I'm not going to bother. I could run it. All right, run it. And you see those are the words with the counts, and that would be sorted, and that would go into word count. But I already have a word count. It was done in the other videos. No sense doing another one. Okay, so we got word count. Next thing is we want to do the stop list, which is word prune. Let's look and see what word prune actually prints out. Word prune. And what are we getting? Whoops! What do we get printed out here? Okay, we're getting this thing printed out. We're just getting the words it's killed. I just don't know if I should put it, write it out to something else. You can. Word prune. Done. Memps. And I'll write it out to. These are the killed.text. These are the words that will have been killed. If you want to save it. And those are the words that got killed. It tells me the word and the document. It prints out the word and the document. Okay, so we've now pruned the database. The next thing is dt.mumps. That's the next thing to run. This is the new code. And it ultimately writes out a line with the inverse document frequency weight, the total number of times the word occurs in the collection, the total number of documents the word occurs in, and the word itself. I don't want to write this to the screen. I want to write this out because I'm going to sort it. So I will say dt.mumps, and I'll write it out to idf.text. Okay. And this takes a little while because it has to read in the stop. Okay, it's done. IDF.text, this is what it looks like. And you can see there's the words. Here is like 10 base T. You can see there's a hyphen missing. That's Ethernet back in those days. So we get, the first value is the inverse document frequency. The second one is the total number of times the word occurs in the collection. And then the total number of documents the word occurs in. So you see like 10 base T occurs in 12 times total in the collection and in 9 separate documents. All right. So what do we want to do with that? We want to sort it. -NR, which means numeric sort. We're going to sort on the first column. There's ways of telling it to sort other columns, but they get a bit tricky to write. So we're going to sort based on the first column in reverse order, so we see the most frequent first, or the biggest numbers first. And the IDF.text is the input, and I'll write the output IDF sorted text as the output. And sort is pretty quick. And then we see it. These are the one, and now we're seeing it in reversed order, sorted by inverse document frequency weight, and 10.97 was the highest value, and it was well, there's several, a number of them at 10.97. There's no particular order to them at this point, but these are the words that ended up with the highest score. The word star. Some of these I wouldn't even recognize now. They're software from years and years ago. But anyway, we move further down. Let's see. There they are, for what they're worth. Again, we've got a very small sample size here. And you can see the columns of the first column is the inverse document frequency. The second column is the number of total number of times in the collection. Third column is the number of documents it occurs in. So as we go down the list here, let's go all the way down to the bottom. And these are the junky words, the ones that ended up with the lowest score. And you can see some of them here we would probably want to go in and add these to our stop list, like the word this. It's got a score of 3.11. It occurred 265 times in 231 documents. And you can get the idea what we're talking about here. A word that it frequently occurs and is spread across a large number of documents is not a good indexing term. We want words that distinguish documents from one another. And a word that occurs in this case here, more than 10% of the collection, is probably, not a good resolving term. And it isn't. The word that you would never search on the word this, unless you were doing a C++ program, I guess, where the word this refers to a pointer. Microcomputer. Now, microcomputer in a lot of collections would be an important term, but in a database about microcomputers, it's pretty common. So it's not really a good indexing term. Industry standard. You can see these things. Anyway, without getting into the details of information retrieval, you can see that some of these are really, the low-numbered ones are easy to see as being junky, like computers and time and evaluations and networks. They might be an important word in another collection, but they're not important in this collection. So there we have it. We've got the inverse document frequency calculation. Now what we would do with that is we would take it and we would go into each document. And we would multiply the number of times each word occurs in each document by its associated inverse document frequency weight. That value would be the weight of the word in the document. And that's much more sensitive. So we then would have, the IDF by itself is the relative weight of the word in the collection. Whereas in the document, we would multiply that weight by the number of times it occurs. So the value in the document term matrix will become a weight of the word in the document rather than the count of the word in the document. The count of the word in the document doesn't really tell us too much. The weight, however, it's a value we can compare from one document to the other. All right, that's enough for today.